Hi, it's Bill. I want to share something I've been working on. MFP is a patching system similar to Pure Data or a Max MSP. Here's a simple Hello World patch. Type M to add a message box with any literal Python data, in this case a Unicode string. Type C to set up a connection from the message box. Type A to drop a marker for auto-placing the next element. Type P to place a print processor, then return to create the connection. Escape switches from edit to operate mode. Click on the message to emit, and it appears in the log tab. This is an all-new UI still in development using Dear Imgui. The old UI was implemented in GTK and Clutter. Here's some screenshots of patches. The descriptions are in the video notes. MFP is implemented in Python with a DSP engine that's written in C. The things I like about it compared to Max and Pure Data are that messages between elements can be any kind of Python data. In fact, Python is barely below the surface of most parts of the app. The patch editing process can be run completely by the keyboard with no mouse interaction needed, and it does exclusively audio and not graphics or other media. Here's a patch I use all the time. It takes a MIDI input and turns it into control voltage outputs for pitch, gate, and modulation to run a hardware synthesizer. This is a mono voice stealer. It has a little complexity because we want to keep track of all the keys that are being held down on a MIDI keyboard and do something smart with the pitch and the gate output, both when the key is pressed and when a key is released. There's not a single right answer, but I like the playability when, if you're holding down multiple keys, releasing one puts the pitch back to the most recently pressed key that's still being held down, but it doesn't re-trigger the envelope, so you get a sort of a pull-off effect. Let's see how this patch implements that. Okay, first let's look at the inputs and outputs just to see what's going on. So the MIDI events come in here. This gets everything, all channels that's connected to the app on the first MIDI connection. The outputs there's 3 DSP outputs. They're the out twiddles that go to the jack outputs of the process. Out twiddle 0 is going to be the pitch CV. Out twiddle 1 is going to be the gate CV. And out twiddle 2 is going to be the modulation CV. MFP can have as many jack inputs and outputs as you tell it on the command line. So when a MIDI note comes in here, it gets processed by the case processor here. It matches on the type of the MIDI event. So case is like route in Pure Data, except it doesn't take a separate address value. It just tests the input against its args and it sends the input to the first matching output. So if the args are type objects, such as Python classes, the input is checked to see if it's the same type as is specified by the argument. For ordinary values, the input is just checked for equality with the value. So in this case, we're checking the type of the input event against these event types, note on, note off, MIDI pitch bend, and MIDI CC. When the processor is created, the argument string here is run through the Python evaluator. So these type names are converted to a tuple of the actual type objects for these different MIDI events. So the last outlet here, just like with route, is the for unmatched inputs. So we're not using that for anything. The next one here is for the MIDI CC continuous controller events for modulation. So the CC events go into this get, which is a built-in to get like an attribute of an object or a dictionary value based on its key or an array element, depending on what the input type is. In this case, it gets the value attribute from a MIDI CC event. That goes into this CCV twiddle helper subpatch here, which converts the integer CC value into a continuous CV signal, and then to the out twiddle. This number box here sort of keeps track of the number. You can see as it changes. You can hear the timbre change there as we change the modulation. So if we open this CCV subpatch, see, we'll say open CCV. So the CCV subpatch you can see here is just a straight line. It takes the message of the integer control continuous controller as on its inlet, divides by 256 to normalize it, uses sig twiddle, which is a helper which takes a message as an input and sends out a constant signal as the output, so just a numeric signal output. There's a slew twiddle here, which just like helps smooth out the sharp edges by putting a 0.1 millisecond slew on it. And then that goes to the patches outlet. So you can see here that the new Imgui UI has this tiled patch display manager that's patterned after Tmux, sort of. Under the window menu here, you can see the different operations you can do with tiles. You can split them, convert them to their own page, swap the contents with each other, and so on. Yeah, so we'll close that. If we go back here, the next MIDI event type here is the MIDI pitch bend. So that goes to this outlet. Again, there's a get to get the pitch bend value. Then this normalizing factor that sort of combines the 14-bit range of the MIDI pitch bend message, then the sort of 10 octave like control voltage range with jacks like -1 to 1 signal rate. So this basically normalizes the MIDI pitch bend down to a value from 0 to 1 that's going to be output by jack, and then goes to sig twiddle again. And then down here it gets added to the pitch that's being used. This is easy to do because these are volt per octave signals as opposed to hertz frequencies. So volt per octave is sort of a standard used by a lot of hardware synths, where the nice thing about it is every semitone is a fixed numeric offset, whereas with hertz, like every octave, like the range of frequencies doubles. So calculating the hertz offset for a semitone bend, pitch bend, is becomes a little bit tricky. So here it's a little bit simpler. You can just add to the offset. So now if we look at the next two, note on and note off, these are this kind of the money events here. They work together to define the pitch and the gate signal. Let's look at the note on first. So that's this first output. Goes into a trigger. Triggered, like in PD, is the kind of a sequencing element that just copies its input to its outputs one at a time. So it goes from right to left, this one, then this one, then this one. And then that, combine that with the depth first evaluation order, and we can kind of predict the order that the patch is going to execute in. So in this case, the first output, so this is, remember, this is the note on event that's come in, like just a MIDI event object, goes out here, hits this message object, so it bangs out the 0, and that 0 goes in to initialize the pitch bend back to 0. So when we have a note on, it resets the pitch bend. Then the second output goes into this track keys helper. This is a sub patch we'll look at in a minute that keeps track of which keys on the keyboard are currently pressed down using the note on, note off events. And then the output of that is a Python dictionary, which has as its keys a tuple of the note number and the MIDI channel that the note is on. And so when we come here, we want to figure out which key we're going to sound. So we pass that dictionary into this func object. So this is where Python is really just very slightly below the surface here. This is just a Python lambda that we put into an object and call it func instead of lambda, just because, why not? The argument here, M, is the message that's coming in on the inlet. If you specified 2 arguments here, there would be 2 inlets. And the output is the result of this Python expression. So this finds the keys of M, which is, M is a dictionary, as I said, and turns that into a list. And then outputs it. So here we have, coming into the get object, we have a list of the keys that are currently being held down, because as a kind of a technicality, the Python dictionary, when you call keys, the list is ordered in the order that the keys were inserted into the dictionary. So the most recent one is last. So we can get array element -1. That's the last element in an array in Python notation. So we'll get the most recently pressed key. And default equals none, so like it means if there is no if there's no value if it's an empty list, then we return none. Then we compare here. This is like sort of a shorthanded case with that routes the input to one of its outputs based on a test. There's a whole bunch of these for like greater than, colon, less than, colon, greater than or equal, colon, whatever. And here, if the input is equal to none, it goes out the leftmost output. So if it's equal to none, what that means is there are no more keys being held down. So we want to send a 0 to the gate output. We want to 0 the gate output, which I'll show you. We'll talk about this sort of sub part in a bit. If the key is not none, it goes out the right outlet. Then we get the 0th element, so that's the note number, the MIDI note number. Remember it was a tuple. The key was a tuple of note number and channel, so we're just discarding the channel here. And then we look at it in this number box, but we also send it to the note twiddle helper. So this is kind of similar to the CCV twiddle helper. It just takes an integer note number and it turns it into a volt per octave frequency or a volt per octave signal that we add with our pitch bend and then send it to the output. So the interesting part here is this track keys helper. Let's see if we can open that. Let's look at this bigger. So track keys looks at node on and node off events. Both of them are passed to it. And here, this is kind of a funny construct, but I think it's kind of interesting. So what it's going to output is this dictionary. var here is a processor that can hold any kind of Python data. So it holds one Python object basically. If you hit it on the left input, it replaces the value of the object and then emits it, unless you hit it with a bang, in which case it just keeps the old value of the object and spits it out. If you hit it on the right inlet with a new object, it sort of stores that new object but doesn't output it. So anyway, so we're going to initialize this var as an empty dictionary representing that there are no keys being held down, right? And that's going to come out. So if we have a note on message that comes in, so we have trigger. So what are we doing here? So this is a trigger. It's a sequencing element. First, we go to this get. We get the key, so that gets the key number from the note on event, and the get on the left outlet is the value that you asked for, and the right outlet copies the input to the output. So that's just helps with these kind of things where you want to fetch multiple values. You can sort of cascade them as we're doing here. So we take the event, we get the key, and it goes down here. Then we pass that to the next get to get the channel. So that's the key and channel for the note on. We put them into a pack. So pack takes the two values and turns them into a list of two values. Then we convert that to a tuple. It needs to be a tuple instead of a list. If you're a Python programmer, you know that lists can't be the keys of dictionaries, only because tuples are immutable. So they can be keys of dictionaries. And then we send that tuple to two places. We send it into a set. It's into the second inlet here, so it's not going to do anything right away, right? Because we have to hit it on a hot inlet for anything to happen. And then we send it also to this delete. So what's going to happen here is if for a note on, the note on event, after it does that, so that's basically the terminus of that pathway, that the tuple representing the key and the channel goes into both of these, the set and the delete. And then basically if it's a note on, we're going to hit this bang. So that outputs this var into the hot inlet of the set, and it sets so this is a dictionary that's coming in, and the key is the second inlet, and the value is the third inlet. So it's going to be setting the key that is the tuple of note number and channel to the value true on the dictionary that's banged out of this. And so just like this var and this var, they were all initialized to empty dictionaries, right? Okay, so what happens then? So then we have a dictionary coming out of this set that has one key set. It's the note channel tuple that goes into this var. So it replaces the value that's there. So now we have a dictionary in there that has this one key that's being held down represented. Then what happens? So then that, since we hit it on the left inlet, that goes immediately out the outlet. So it goes out to the rest, to back to the main patch, but it also goes to the right inlet of these two vars. So basically all three of these vars are synced. They all have the same value in them. So then what happens is when there's a new thing that comes in, we extract the key and queue it up for both adding and subtracting. And then if it's a note on, we add it to the dictionary. If it's a note off, we go the other way, and the second trigger bangs this var, which hits a delete. So it deletes that key from the dictionary and then stores the dictionary back in here and then propagates it to sync back up with the other two as it sends it out to the outlet. This kind of, it's kind of a typical control flow using trigger and case to kind of put the stuff together. So let's go back to the main patch. So that's track keys. So basically each time a note on or note off comes in, we're going to get a dictionary out of track keys that's going to say which keys are currently being pressed. And then we have gone through the rest of this stuff. So like you can see the pitch, like if we have a note on, let's see, we can see it. The note number is reflected in the number box right there. If we do a bend, the pitch bend changes, but the note number doesn't change. We're staying with the same note that whole time. And okay, and finally, let's look at the gate output. So basically, for note on, we always bang this 110. So this goes basically is input to the line twiddle that controls the outlet. It goes to a value of 1 over a period of 10 milliseconds. And you can have a sequence of these things in here, to do a multi-part envelope or whatever. But for controlling this gate, we're just going to 1 in 10 milliseconds. And then when there's no keys left being held down, then this is going to be equal to none. And then we're going to turn the gate off. So, yeah, I'll stop there. Thanks for sticking with it. MFP is free software. You can find it on GitHub. Be sure to read the README for how to launch with the new Imgui backend. Thanks.